Okay, so we had gone over yesterday how to use elimination in addition to substitution. We started with substitution. We talked about now elimination. Then we went over like what we did on your bell ringer, which is the cost function versus revenue function and figuring out like what the break-even cost would be. Now we're going to finish it up and we're going to go over a couple of mixture problems. So there's times where you might have to mix different quantities or different proportional amounts of things in order to create something. So a lot of times, like in chemistry, we might mix a little bit of this and a little bit of that in order to have something happen. But you don't always just do like a 1-to-1 ratio where you take the exact same amounts of the two things that you're working with. So we're going to go over how do we work with a mixture problem and still use the system of equations like we've been talking about in order to solve. So usually when we do mixture problems, it's sometimes helpful to use a table to kind of organize the things that they're talking about and like how we can kind of sort out the numbers so that we can see what we're missing and what we need. So this table here at the top is just kind of like a generic one that you could use for any problem, where the left like first side column is talking about what exactly you're mixing. So like the different items or the different things that you're trying to put together. And then the number of units would go next, the value per unit, and then the total of each unit. So all of those things are kind of just giving you like headings so that when you go to a problem, you can kind of customize it for what maybe works best for your situation. So on this first example that I have, I already filled out the chart for you, but I want us to read through the problem so we can see where we got all these numbers from. So it says that a chemist is working on a flu vaccine and needs to mix 10% sodium iodine solution with 60% sodium iodine solution. I'm going to stop here for just a second. They're talking about percentages. When we're working with a percentage, what do we need to do to that number in order to actually calculate with it? You have to move the decimal two places, right? We never will take something times, like if it was 50% off, I would never take the cost of the item times 50 because that's not a true representation of what happened there. I would take it times 0.5 instead to get it to cut in half. So if you look at my table down here, the 10% and the 60% from up here are here in the chart, the 0.10 and the 0.60. So how they decided to put their chart in up there or on the screen here is that we have milliliters first, the percentage is in the second one, and then they've got that total on the other side. But that's where those numbers went, okay? So I'm going to keep reading. It says to obtain 50 milliliters, okay? So 50 milliliters is the mixture that we're trying to create. So that's down here in my chart. It's not letting me highlight the 5, but it's over there. And then we want to make a 30% sodium iodine solution. So we're back to another percentage, and that's again being written as 0.3. So they want us to figure out how many milliliters of the 10% and the 60% solution do we need in order to get this mixture just right. So what we can do is think about the two things that we're mixing as our variables, x and y. And so when we look at our chart down here, milliliters is how much of each thing that they're mixing together. We're just going to call one of them solution 1 and one solution 2. And we're going to mix those two things together, but we're calling one x and we're calling the other one y. When we mix them together, I want a total of 50 milliliters. That's how much I want my mixture to come out to be. My second column is all those percentages of each individual solution and of my mixture solution. And then your total column over here is kind of what we're going to start to use when we're trying to write out a formula. So the first formula that they wrote down here, this x plus y equals 50, that all comes from your milliliters. I'm adding my two solutions together and I want it to equal 50 milliliters, but I don't know, do I need 5 of the first solution and 45 of the second one? Do I need 20 and 20 or 20 and 30? Do I need something else like split-wise, like 50-50 or something to get to 50? The percentages, I'm not going to necessarily just use the 0.10, the 0.6, and the 0.3 because remember, I'm taking this percent as a solution times however many milliliters. So actually this equation here came from the total column. So the total column is written as that 0.10, the percentage, times x for this first solution, and then 0.6 times y for the second solution. And then where they got this 15 from is we know the mixture needs to be 50 milliliters, and we also know that the mixed solution should be 30%. And so they multiply those two numbers together. That's how they get the 15. So these are your two equations. Now what we're going to do is work with them to solve for x and y. And you guys can kind of choose at this point if you'd rather use substitution or elimination. It doesn't really matter which method you use. You should be able to solve this either way. What would you guys like me to use, substitution or elimination? Anyone have a preference?
Elimination.
I would probably choose elimination only because I like elimination better than substitution. Okay, so let's go that route. Let's get rid of our x's. Okay, so I need this top x to look the same as the bottom one. So I need a 0.10 in front of it, but I'm also going to make it negative. That way they're opposite signs. So I'm going to take this top equation here. I'm going to take that times negative 0.10, or you could just think of it as negative 0.1. You don't have to have the 0. So then if I do that, my top equation would now say negative 0.10x minus 0.10y. And then what's 50 times 0.1? Negative 0.1. Or you could think of it, what's 10% of 50?
0.5.
Close. Not 0.5, just
5.
Just 5. Yeah. Okay, so just 5 there. And the second equation is going to stay as is. So I'm just going to copy that down. Okay, if I add these equations together, my x's eliminate. What do I have left for my y's? What's negative 0.1 plus 0.6? 0.5. Y. 5 plus 15 would be 20. Then you're going to divide by 0.5. So how much do we get for y?
40.
Hold on. What did I? Oh. Back up. Hold on a second. This 5 here should be negative 5 because we took it times a negative 0.10. So this shouldn't be 20. It should be 10. That's my mistake. I missed my negative sign up there. So what's 10 divided by 0.5? 20. Okay, so back in our context of our problem, y represented solution number 2. I need 20 milliliters of that. So I'm just going to write over here, I need 20 milliliters of solution, I'm going to abbreviate that, 2. But I still need to figure out how many I need of solution 1. So what should I do with this 20? Plug it back into one of the original equations. It doesn't matter which one you guys go back into, but I would probably use the top one because it's just x plus y equals 50. So if I put this equation now and it says x plus 20 equals 50, how many milliliters of the other solution do I need? 30, right? So I'm going to write up here now, I need 30 milliliters of solution 1. Questions on how we did that? Okay. We've got one last example here, and it's similar to what we just talked about. We're mixing percentages here. I'm going to help you guys get your chart set up, and I'll give you a little bit of time to see if you can set up your equations and solve it here. So I'm just going to draw out a chart like what we had on the last one. Okay, so this time, what's our measurement for this solution? Like the last one was milliliters. What is it for this one? Ounces. So I'm going to put OZ in that one for ounces. I'm still dealing with percentages, so I'm going to put percent. And then this last one is still going to be total. How many things are we mixing together? Two different things, okay? Because it says 50%. How many ounces of a 50% alcohol solution must be mixed with 80 ounces? So there's two quantities that they're trying to mix together. So we can still call it solution 1, solution 2. And then your mixture. Okay, so we've got kind of the bones of our table created. Now let's fill in numbers that we have here. So let's just start out. It says how many ounces of a 50% alcohol solution must be mixed with 80 ounces of a 20% alcohol solution to make a 40% solution. I have 3 percentages here. So let's just fill in our percent column first. How would I write 50% as a decimal? 0.5, 20%, and then 40%. And why is 0.4 the last one? Yeah, that's what we're trying to get the mixture to equal. Okay, so when you're reading the problem too, make sure you can distinguish, okay, I'm mixing this guy and this guy to get this final amount. So that's why the 40% goes in the mixture column. All right, do we know how many ounces we're using of the 50%? No. Okay, so I'm going to call that X. Do we know how many ounces we're using of the 20%? Yeah, how many? 80. Do we know how many ounces we want for my mixture? No. So this is going to be where my other variable goes. So the variable's in a different spot for this one than it was in the last one. That's not a huge deal though. We'll talk about how to handle that. So then to find your total column, if you remember what I did on the last one is I multiplied. So I'm taking X times 0.5. So I'm just going to write that as 0.5X. What would be 80 times 0.2? 16. And then how would I write my last one here? Good. Okay, now I'm going to look at my equations. I use like this column to help me write an equation, and I use this column to write an equation. And usually when we have it set up like this in a table, you're always adding the first two and setting it equal to the last one. So I'm just going to draw like big plus signs and a big equal sign in there. So your two equations should say x plus 80 equals y, and then 0.5 x plus 16 equals 0.4y. If you want to use elimination again, you might want to rearrange and like have the x's and the y's be on the right side or the left side of the equation, have the equal sign, have just the plain numbers. You could rearrange that. You could also use substitution here if you'd like, because they do have that first one solved for y. It's just written backwards. So I'm going to give you a couple of minutes. I want you to see what you can do with those two equations and see if you can figure out how many ounces we need to get that x and y. And that's why I took this times and what's the other match here. If I wanted to get rid of y's, then I would have multiplied by 8.6 instead. Okay. To get the same. It doesn't really matter which one you get rid of, you just have to make a choice. Okay. All right, I'm going to start working through this. Now, just to show you substitution again, because I did the last one with elimination, I'm going to use substitution here, just so you can kind of see how this one works. You don't have to use substitution, though. If you guys use elimination, you should be able to get the same answer that I got. The only reason why I'm going to maybe use substitution here is because this top equation is solved for y. It's just written backwards. So I took this whole x plus 80, and I'm going to plug that in for the y on my second equation. So the second equation is now going to say 0.5 x plus 16 equals 0.4 times x plus 80. Okay, on the right-hand side of my equal sign there, I will have to distribute. So this said, do you need more? Yeah, I do. Okay, so I would distribute the 0.4 to the x plus 80. So this would say 0.5x plus 16 equals 0.4x, and then someone double check me here. 0.4 times 80 would be 20, I believe, but can someone check that for me? 32? Yeah. Where did I get 20 from? Oh, because I was thinking of dividing by... I was thinking that 0.4 was a fourth for some reason, and it's not. Okay, not 20. 32, you said. I need to go home. Okay, now let's solve for the x. So I'm going to move some things around. I'm going to move the 0.4 over here to the left, so that'd be 0.1x. And if I move the 16 over to the right side, that would be 16. Okay, and what's 16 divided by 0.1? 160. So x would be 160 ounces. So that would be for solution 1, which is what they're asking for in this problem. Because the problem up there says how many ounces of the 50% alcohol solution needs to be used. Well, we said x was for the 50%, so this is actually the answer that they wanted here. But if they wanted both, or they wanted to know how much the mixture needed to be too, how many ounces for this total mixture, then we could still add that on. So to find y, if you needed to, you would just come back up here to this first equation. You would take 160 plus 80, which would be 240 ounces, and that would be for y. So they might ask for that as well. This problem really only needed the 160 for their answer, but it should also check out if you were to just plug it back in and solve for y. Questions on that last mixture problem?